Good evening. This video is going to review how to perform calculations to determine the change in enthalpy for a target reaction using step reactions. So basically, with Hess's law, it proves that enthalpy is a state function, meaning that the enthalpy of a reaction, it doesn't matter if you calculate it in one step or many steps, you're still going to arrive at the same answer. So we're going to calculate the enthalpy of our target reaction, which is phosphorus pentachloride yielding phosphorus trichloride and chlorine gas. We have two step reactions that include the reaction of tetraphosphorus with chlorine to yield phosphorus trichloride, and another step reaction in which we have phosphorus pentachloride reacting to yield tetraphosphorus and chlorine gas. Notice that these reactions are all already balanced. And so what we need to do is we need to look at our target reaction. In our target reaction, we have PCl5 on the reactant side, and on the product side, we have PCl3 and Cl2. So what we have to do is we have to rearrange our step reactions such that when we add them together, we end up with our target reaction, meaning that there's 1 mole of PCl5 on the left, there's 1 mole of PCl3 on the right, and there's 1 mole of Cl2 on the right. So how do we do this? Well, if you need to, you reverse the reaction. If you need to reduce the coefficients on the reaction, then you can do so by dividing. If you need to increase the coefficients on a reaction, you can do so by multiplying. Anything you do to the reaction, you have to do to delta H. If you flip the reaction, then you have to flip the sign on delta H. So if it's negative, it becomes positive. If it's positive, it becomes negative. If you multiply the reaction by any number, you have to multiply delta H by that same number. And if you have to divide by any number, then you need to divide delta H by the same number. So let's look at our first step reaction. And let's look for some common compounds in that reaction that are present in the target reaction. So in this first step reaction, we have two common compounds. They are PCl3 and Cl2. The P4 is just similar to your spectator ion that you see in net ionic equations. Because generally we want to get those to cancel out. If they are on opposite sides of the yield arrow, they will cancel. It's kind of like something being on opposite sides of an equal sign. If they're on opposite sides, we can divide or subtract them away, and if they're in equal amounts, then they're going to cancel out. So in this case, because we do have PCl3 in the product side, and PCl3 is in the product side on our target reaction, we're going to leave this reaction as it is, because if you look at the second target reaction, there is some chlorine on the product side. There is also P4 on the product side, which would allow us to cancel out the P4 in the previous equation. There is also PCl5 on the reactant side, which is what we need. So we're going to leave these reactions written as is. However, you will notice that you only need 1 mole of PCl3 and you have 4. And you only need 1 mole of PCl5 and you have 4. So you have two choices. You can go ahead and combine all of your reactions as they are, and then you can divide at the end, or you can initially divide your reactions, and you would need to divide everything by 4. So you would end up with 1/4 P4 plus 6/4 Cl2, yielding PCl3. And then, of course, our delta H will be cut by 4. You would do the same thing for the second reaction. You cut it by 4, so you end up with PCl5, yielding 1/4 P4 plus 10/4 Cl2. If you are not a fan of fractions, then you can go ahead and combine your reactions and then divide at the end to get your target reaction. So now that I have done this, and I have now 1 mole of PCl3 and 1 mole of PCl5, I can then go through and cancel out what cancels. So the 1/4 P4 goes away. And I almost forgot, we're going to divide this by 4 as well. All right, and then we have 10/4 of Cl2 on the product side, and we have 6/4 of Cl2 on the reactants. So all of the 6/4 is going to go away, and we're going to subtract that from 10/4, which is going to leave us with 4 out of 4. And we know 4 out of 4 is the same thing as 1. So then we're going to go through and we're going to write our reaction of what's left. We have PCl5 yielding PCl3 plus Cl2. Because remember, 4/4 reduces down to 1. So we've literally combined our two reactions. And by combining our two reactions, we're also going to combine our two delta H's. So if you divide negative 24.39 by 4, you should get negative 609.75. And then you're going to add that to your 3438 divided by 4, which is going to be 859.5. Signs don't change because we did not reverse any of our reactions. So your final answer to 4 sig figs is 249.8 kilojoules. Okay, now I'm going to show you how to calculate in the absence of fractions. So I've cleared off our board and we're going to go through without the use of fractions. We already determined that we do not need to reverse our reactions in any way, shape, or form. So we're going to go ahead and just add these two reactions together. And again here, the P4 will cancel out. Our chlorines will reduce from 6 on the left and 10 on the right to none on the left and 4 on the right. Everything else will remain the same, and our new reaction will be 4 PCl5 yielding 4 PCl3 plus 4 Cl2. And then we're literally going to add our delta H's together. We're going to add negative 2439 kilojoules plus our positive 3438 kilojoules. And when we add those two together, we're going to get 999 kilojoules. And then we need to divide everything by 4 so that we can reduce those coefficients down to 1. So we're going to divide that by 4, and you still end up with your 249.8 kilojoules. So again, you can use fractions or you can wait until the end and divide. Look at our second example. In this reaction, you have 2 moles of carbon dioxide reacting with 1 mole of water to produce 2 moles of C2H2 and 5/2 moles of O2. Excuse the format. For some reason, delta H got shifted, but for the first reaction, the step reaction, we have C2H2 on the left, and in our target reaction, C2H2 needs to be on the right. So the first thing we notice is that we're going to need to flip that reaction. We only need 1 mole of C2H2. We have 1 mole of C2H2, so we're going to go ahead and flip this reaction so that it is C2H6 yielding C2H2 plus 2H2. So in flipping that, then you have to make sure that you go and you flip the sign of this to be positive. So now that I have a positive delta H, because I flipped this reaction, we're going to look at the second step reaction. We have water reacting to produce hydrogen gas and 1/2 of oxygen gas. The water is on the left-hand side, and the water is on the left-hand side in our target reaction. And there's only 1 mole in the step reaction, and there's 1 mole in our target reaction. So we're going to leave this as is. And we're going to literally just write it over H2O yields H2 plus 1/2 O2. And then our third reaction, so delta H stays the same. In our third reaction, we have 2 moles of C2H6 on the left plus 7 moles of O2 on the left, yielding 4 moles of CO2 and 6 moles of H2O. Well, the first thing we notice is that we have to flip this reaction because we need carbon dioxide on the left-hand side. The other thing that we should notice is that we have to cut everything in half because we only need 2 moles of carbon dioxide and we have 4. So we're going to go ahead and do that all in one swoop. And so on the left we have 2 CO2 plus 3 H2O yields C2H6 plus 7 halves O2. So we have now flipped this reaction and we have now cut everything in half. So we're going to change this to a positive, and we need to divide that by 2. So if we get ready to combine our reactions, there's a couple things we're going to notice. Now our middle reaction doesn't work because we need this water to only have 1 mole on the left-hand side. And the way everything is written now, there are 4 moles will result on the left-hand side. We also need 5/2 mole of O2 on the right-hand side. And as it is written now, we will end up with 8/2 of O2 on the left side. So what we notice that needs to happen is, 1, we need to flip that reaction. And we need enough H2 to cancel out the H2 in the very first reaction. So what we're going to do is we're going to flip it. And we're actually going to have to multiply this one by 2. So I'm going to write it in a different color so that you see the flipping. And we end up with 2H2 plus 2 over 2 O2 yielding 2H2O. And because we flipped the reaction, the sign is now negative, and we also multiplied it by 2. Okay? So now we can go through, and we know that this reaction is gone. And we can also go through and cancel out what reduces. So the 2H2 here and the 2H2 here cancel out. We have 2H2O here that's going to cancel, and this is going to reduce down to 1 because 3 to minus 2 is going to give us our 1 mole of water left over. Here we have 2.5 O2 molecules, and it's going to reduce this 7.5, down to 5.5. And so now we can write our overall reaction because, don't forget, C2H6 cancels out. And now we can write our overall reaction. And at this point, our overall reaction is going to be our target reaction. We have 2 CO2 remaining plus our H2O remaining, yielding our C2H2 and our 5 halves O2. So now we have the reaction that we need, and we have flipped all of our signs, we have divided, we have multiplied. Now we just need to combine everything. And we will have our overall delta H. So I'm going to do that on the next slide. And we're going to have a positive 94.5 plus our negative 71.2 times 2 plus our 566 divided by 2. And all of that should add together to give you 235 kilojoules. Now again, if you don't want to deal with fractions, then you could initially multiply everything up so that you have whole numbers, and then at the very end you can go back and then divide back down so that you have the numbers that you need for your target reaction. If you have questions, please feel free to email me and I can answer those questions for you. You are now responsible for questions 3 through 12, and those are due when you come to class next week.